Thank you for the nice introduction, Lewis. Actually, I was also a postdoc at the Fields briefly, so this is another homecoming in some sense. So this is all very nice. Yeah, so thanks, first of all, to the organizers for giving me the opportunity to speak at this very nice workshop. I have very much enjoyed the talk so far. So the topic of this talk is the global rigidity of periodic frameworks. And I would like to present some new results that I have obtained recently in joint work with Victoria Kaszanitzy and Csaba. So they are both in Budapest. And in particular, I would like to present a combinatorial characterization of generic, globally rigid, periodic body-bar frameworks with a fixed lattice representation. So this is a periodic analog of the well-known result of Bob Connelly, Tibor Jordan, and Walter Whiteley, who proved this combinatorial characterization of generic finite body-bar frameworks some time ago. Okay, so here's, oops, I should switch slides. Yes, okay, so here's my quick outline. I will start by reviewing the basic definitions of rigidity and global rigidity for periodic frameworks. And I will mention some of the key results in this area. And then I will mention the key result really that we found. So this result says that vertex-redundant rigidity for generic periodic frameworks implies their global rigidity. So this is a periodic analog of a recent result of Schulze and Tanigawa, who proved this for finite frameworks. And this is a very useful observation, and we managed to adapt this to the periodic setting. And this result allows us to obtain this combinatorial characterization of generic, globally rigid periodic body-bar frameworks very easily. Okay, so the real main result here is that the vertex-redundant rigidity for periodic frameworks implies the global rigidity. Okay, and then I will finish with some open problems in this area. Okay, so let me start with the background. So the starting point here is that we have a group. I will always call the group gamma, and it's isomorphic to z to the k. So this is the periodicity here. And then I would like to define this gamma labeled graph. This is the same as a gain graph as Daniel Bernstein and others. I think Derek and others have mentioned this before. Anyway, let me remind you of the definition here. So a gamma labeled graph is just a pair of a finite directed multigraph G and a map psi that assigns elements of the group to the edges. And so this gamma labeled graph lifts in a natural way to a periodic graph, a k-periodic graph. And so this gamma labeled graph really encodes this infinite periodic structure, as Daniel has already explained in his talk in particular. Here we assume that G has no parallel edges with the same label, because if we had those edges, they would lift then to a periodic multigraph. We don't want that. And we also don't want any loops in the gamma labeled graph. This is because when you lift, so to speak, the loop, then that gives you an edge that connects two vertices in the same vertex orbit. And we don't want that either, because we will look at periodic frameworks with a fixed lattice representation. And so there, whenever you have an edge between two vertices in the same orbit, that distance is already automatically fixed by the fixed lattice. So a loop of this kind would be redundant, and so we don't have loops here. Okay, and so given such a gamma labeled graph, as I said, this lifts naturally to a k-periodic graph. So we get the covering of this gamma labeled graph, which I call G tilde here. And so you get G tilde by setting up these infinite sets. And of course, gamma here acts naturally on these sets. Okay, I will show you an example in just a minute. Before I do that, let me remind you of yet another important definition here for gamma labeled graphs. Again, this is something that Daniel also introduced, but let me remind you. So suppose you have a closed walk in the gamma labeled graph, then the gain of this walk you just obtain by taking the sum of all the group labels of these edges with the condition that when you walk along an edge backwards, then you have to take the negative or the inverse of that group label. And so this gives you a group element, the gain of this closed walk. And for a given subgraph H of the gamma label graph, we can look at all closed walks and look at all their gains. And these generate a group, and the rank of this group is called the rank of this subgraph. So intuitively, this rank, of course, tells you how the edges of this gamma label graph wrap around the fundamental cell of the lattice, so to speak. Right? So if the rank is 0, you just have a finite piece sitting in the fundamental cell. If the rank is 1, then it wraps around in one way, and the rank is 2, then it wraps around in 2 ways, and so on. So here's the example. On the right, you see a gamma labeled graph, and on the left, the corresponding periodic graph. In fact, here you have already chosen positions for the vertices. So you see a gamma labeled framework on the right. So just a gamma labeled graph together with the configuration. And on the left, you see the covering. So this is an L periodic framework G tilde P tilde. So here it is important to remember that the lattice will always be fixed in this talk. So here the lattice is given by these two vectors. The lattice should be non-degenerate. So I call this non-singular here. So this means that L of gamma has rank K. Remember, the underlying group here is Z to the K. Right? So this is K. And here K is actually at most D. Okay. If K is equal to D, then this definition of a periodic framework that I give here is actually exactly the definition that was established by Cyprian Portea and Iliana Stranu, who have done a lot of the fundamental work for analyzing the rigidity of periodic frameworks. Here we have just have a very minor extension of their definition, and namely we allow this K here to also be less than D. So for example, if you look at this periodic framework up here, we can think of it as lying in 3-dimensional space. So D would be 3, even though it's only 2 periodic, right? So that the periodicity here only has rank 2. Okay, so this is just a minor adjustment of the definition of Portea and Strain. Okay, so we have this periodic framework and the corresponding gamma labeled quotient framework, so to speak. How do we define periodic local and global rigidity? Well, we do it exactly in the same way as we do for finite frameworks. So we say that 2 periodic frameworks, so lattice L is always fixed, are equivalent if corresponding edge lengths are fixed. And of course, they're congruent if all distances between any pair of vertices are fixed. And then we say that a periodic framework is rigid if in some open neighborhood of the configuration, every periodic framework that is equivalent to this given framework is also congruent to the original framework. And of course, it is globally rigid if this framework GP here is the only framework with a given edge length, right? So if every periodic framework that is equivalent to GP is in fact congruent to GP. So these are very standard definitions. For those of you who have not worked with periodic frameworks yet, let me just show you a little example here. So here we have a periodic framework in the plane with rank 2 periodicity. So the lattice here is just this square grid. The gamma labeled framework has just 2 vertices, so that is 2 vertex orbits. And you see the rank here of this gamma labeled graph is 1. Right, there's only 1 closed walk, and the gain here is non-trivial, it's 1, 0. And so you have rank 2 periodicity, but the gamma label graph only has rank 1. So this means that you get these infinitely many strip frameworks here, right? So the strip framework is somewhat repeated periodically, infinitely often. And this framework is disconnected, of course, but it is still rigid. Okay, this may be a bit strange, but remember that whenever you have a vertex orbit, then because the lattice is fixed, all the vertices in the same vertex orbit are actually implicitly joined with edges. Okay, and if you think of it that way, then I think it doesn't look so strange anymore. But this framework is not globally rigid. Okay, so clearly we can take each of these infinite strip frameworks here, and we can just flip each of these strips in a periodic fashion, and that gives us an equivalent, but of course non-congruent realization, because the lattice here, of course, is fixed. Okay, so I hope that makes sense. Feel free to of course ask questions. I cannot see the chat, but Lewis said he will interrupt me if there are any questions there. Okay, so how do we analyze periodic local and global rigidity? Well, we look at this gamma labeled graph, and we do this standard thing. We look at the squared edge length function, so which I call here the rigidity map. So here this map just takes any configuration of the vertices of this gamma label graph and maps it to the length of the edges. And of course, we can also look at the rigidity map for the complete gamma label graph on the vertex set V. So this is the rigidity map that I denote here by FVL, where V is just the underlying vertex set. What is the complete gamma label graph? Well, here you have that vertex set V, and you put all possible edges among these vertices V. So all edges of the form UV, where U and V are vertices in the set, and all possible group labels. Okay, and then we can easily see that the following proposition is true. So if you have a periodic framework and it's a quotient gamma labeled framework, then this periodic framework is globally rigid, if and only if for every configuration Q of the vertices in the gamma labeled framework, we have this implication here, right? So if corresponding edge length in this quotient structure are the same, then actually all the distances are the same. Okay, so and of course similarly for local rigidity, that this holds, this proposition follows immediately from the definition of periodicity. Okay, so we can just analyze the quotient gamma labeled framework rather than the lifting or the covering. Okay, and in fact we can then define this gamma labeled framework G psi P as globally rigid if, well, for every configuration Q here, right, we have this implication. Okay, this is fairly standard, I think. Let me now review some basic results in the area of periodic local and global rigidity, and I will particularly focus on generic results, so combinatorial characterizations. And let me here start with local rigidity. So first of all, because we're interested in well, combinatorial results, let me first introduce the basic notion of genericity. So gamma labeled framework is called generic if the set of coordinates are algebraically independent over the rationals, and of course an L periodic framework, so the covering of the gamma labeled framework is generic if the corresponding quotient framework is generic. Then we have the first basic result, which was proved by Elissa Ross, and this was slightly extended by myself and Victoria and Kaszanitzy. So this theorem says that if you have a gamma labeled framework that is generic and it has not too few vertices, then this framework is rigid, so locally rigid, if and only if the rank of this rigidity map that we just looked at in the previous slide is equal to this number. So Elissa actually proved this in the case where K is equal to D, so where the rank of the periodicity K is equal to the dimension. In that case, of course, if D is equal to K, then this binomial coefficient here vanishes. And so we get this top count here of dV minus D. And of course, that's exactly the count you would expect because for a periodic framework with a fixed lattice, the trivial motions is a d-dimensional space, right? So it's the D translations. And so here we just slightly extended this to the case where K can be less than D. And if K is much less than D, then there are some additional rotations coming back as trivial motions. Okay, so that is quite straightforward. I should say here that for this particular theorem, we don't need this strong notion of genericity that I defined up here. So here it would be sufficient to assume that the configuration here is just a regular point of this rigidity map. So it has this Jacobian here has maximum rank because this theorem is proved by adapting the method of Asimov and Roth. But later we will of course focus on global rigidity, and there we will need this stronger notion of genericity. So let me go with that. Okay, another little remark here. So this Jacobian of this rigidity map is of course the periodic rigidity matrix here for frameworks on a fixed lattice. This rigidity matrix is actually a specialization of the rigidity matrix that was established by Cyprian and Ileana some time ago, who established a rigidity matrix for periodic frameworks on a flexible lattice. So there you have additional columns that correspond to the additional flexibility of the lattice. So here, when we fix the lattice, of course, our matrix becomes simpler. So we have a special case of their matrix, if you like. Okay, and so using this, Elissa gave a Lemma type or Polacek-Geiringer type result for periodic frameworks in the plane, again with a lattice fixed. So she showed that generic periodic framework in the plane is rigid if and only if the corresponding quotient graph contains a spanning subgraph that satisfies these conditions. Okay, so we need the top count 2v minus 2, that's clear. And then we have these sparsity conditions here that split into two parts. So if you have a subgraph of the quotient graph that is of rank 0, right? So this means that this graph doesn't wrap around at all around the fundamental cell, then really you have to apply the standard Lemma type subgraph count. But otherwise, of course, you use this adapted periodic count. Okay. Also, of course, you can look at this more generally when you allow the lattice to flex. So this makes the problem more difficult. But here we also have a Lemma type theorem. This was established by Justin Meierstein and Louis Ferran again some time ago. Okay, let's go back to the fixed lattice. So what can we say about higher dimensions? Of course, we have necessary Maxwell type counts, right? So we have the top count E equal to dv minus d if the periodicity has a rank equal to the dimension. And you can easily establish subgraph counts similarly to the conditions here. But we do not, of course, have necessary and sufficient conditions because, well, this problem of characterizing generic rigidity in dimensions at least 3 is open, of course, for finite frameworks. So it's also open for periodic frameworks. Okay, one side comment here. So we do actually have very nice results if we change our problem a little bit. So if we're only interested in finding rigid periodic frameworks for some labeling of the edges, so if we omit the labels of the quotient graph or the gamma label graph from the input, then actually we have complete combinatorial characterizations for generic rigidity in all dimensions. So this was done for the fixed lattice quite some time ago by Walter Whiteley, and it was done for the flexible lattice again by Cyprian and Ileana. But I do not want to focus on this here in this talk. So in our talk, our starting structure is always a gamma labeled framework. So where we have labels, group labels on the edges. Okay.
Okay, so Bernd, there's something in the chat. So Jim asks, in the definition of genericity for periodic frameworks, does the lattice play a role? It's a good question.
No. So basically here we only need the configuration, but we want the lattice to be non-degenerate. So we want it to be a full rank, so to speak. I think if you consider a flexible lattice, then you have to be more careful.
Sure. I mean, but in your setup, if you make an affine transformation of the whole picture, including your fixed lattice, do you preserve the interesting properties?
Yeah, I think it's okay with a fixed lattice.
Does the lattice have to be generic?
I think for the fixed lattice, it only has to be non-singular. So non-degenerate. So, okay, I have to think about this.
So if it's similar to the global rigidity you did with periodic stuff, I think your assumption here would be that you're generic with respect to the rationals, the field with the rationals and the coefficients of the lattice, right?
So in flexible lattice, it absolutely needs to be, because you have affine invariance of the rigidity matrix rank, but not necessarily of global rigidity properties, just like finitely.
Yeah, yeah. So I mean, maybe you're assuming here that the lattice coefficients are rational or something.
Yeah, there may also be a difference between, whether you consider global or local rigidity.
Yeah.
Okay, I would have to check. I think, I thought that for local rigidity, actually, it's okay. It doesn't matter, but I'm not 100% sure. Yeah. But yeah, so for the flexible lattice, you need it. For global rigidity, it may also be a different story. Anyway, I should check. Thank you for the question. Does anyone else know on the call?
Okay, so Jim says thanks. He's simulating a student, I think, and not demuting himself.
Right. Okay. Well, thanks for asking.
My microphone is working now. Sorry, it wasn't working there. I was desperately trying to talk, but it.
Right. Okay. Right. So we were talking about local rigidity still. So what can we say about local rigidity in higher dimensions? So as we all know, for the finite case, if we consider higher dimensions, then dimensions at least 3, then we do not have a combinatorial characterization of generic rigidity. But of course, we have essentially complete combinatorial theory for special types of frameworks, namely body bar frameworks and body hinge frameworks and molecular frameworks. And all these frameworks, of course, play an important role in applications. Now, in the periodic case, the situation is not quite so nice, but we do have a complete combinatorial characterization for rigidity of periodic frameworks, of periodic body bar frameworks. So we don't know if this extends to body hinge and molecular and so on, but we do have a nice characterization for body bar. And this is a result of Kaszanitzy, I would like to mention, because later we will talk about global rigidity of body bar frameworks. So what is a body bar framework? Most of you probably know this. So it's just a collection of rigid bodies, and they are connected by bars pairwise. And so the underlying combinatorial structure here is a multigraph, as you can see on the left, where every vertex corresponds to a four-dimensional body. And whenever you have such a body, we can model it as a bar joint framework, right? Just take a complete framework, basically. And the way we do this here is that whenever two bodies are connected by, let's say, by an edge, so let's say you have bodies U and V, and it's connected by an edge, then we create a new vertex for body U and a new vertex for body V, and then join these vertices here by this edge. So by doing that, we ensure that all these edges connecting the bodies are actually disjoint, so they don't share any vertices. Okay, so this is a model of a body bar framework. We can use exactly the same model to model a periodic body bar framework. So here, rather than starting with a multigraph, we start with a gamma labeled multigraph, so to speak. Okay, so here we have a gamma labeled graph. It is allowed to have loops as long as it has a non-trivial group label. And it is also allowed to have parallel edges with equal labels. And that then lifts, of course, to a periodic multigraph that has no loops, but it may have parallel edges. So this multigraph looks exactly like this, this graph here on the left, except that now it is periodic. And then we can do exactly this, this type of construction here to model our periodic body bar framework. There's only one slight technical thing. So if you have two bodies, let's say, that in the same body orbit, and they are connected by an edge, then you do not want to just put a single vertex here and connect it with its copy under the periodicity, because then you actually get, two vertices in the same vertex orbit that are joined by an edge. And remember, because the lattice is fixed, this would be a redundant edge, right? This this distance would already be fixed by the lattice. So rather than doing this, if you have two bodies that are connected by an edge, you would create two vertices on each body, and and you would actually add an edge of this form. Okay, so you avoid actually having these redundant edges. Okay, but this is just a little technical point. So otherwise, you can construct body bar frameworks in the periodic case exactly as we do in the finite case. Okay, and here's the result of Kaszanitzy. So Kaszanitzy proved that if you have a generic body bar framework that is periodic, then it is rigid, so locally rigid in R to the D, if and only if the corresponding quotient graph has a spanning subgraph that satisfies these counts. And again, these are the natural counts here, really. So notice that if D is equal to K, then again, this disappears and you get this D plus 1 choose 2 times D minus D count, which you would expect. And of course, similarly for the subgraph counts. I should mention here that the special case of this theorem for D equals 3 was actually proved by Elissa, but then it was Kaszanitzy who was able to extend this to all dimensions. So this is nice. This is a nice result in higher dimensions for periodic local rigidity. Unlike the finite framework case, this is unclear whether this extends to body-hinged and molecular frameworks. So these are still open problems. And we also don't have any extensions of this result yet for periodic frameworks with flexible lattices. So that's lots of open questions still. What we do have, again, this is a side comment here, I guess, is a complete characterization in the case where we again omit the labels, the group labels of the edges. Okay, so if you just want to find a rigid periodic framework for some labeling of the edges of the quotient graph, then there is a characterization for generic rigidity of body bar frameworks for the flexible lattice in all dimensions. And this was done by Cyprian, Iliana, and Kaszanitzy. Okay, but again, this is not the setting we're looking at in this talk. Okay, what do we know about periodic global rigidity? Well, actually not so much. So problems in this area of periodic global rigidity seemed basically out of reach for quite some time, and no results were obtained, at least on the generic level or the combinatorial characterization level, until a couple of years ago or so. And what changed a couple of years ago was that Kaszanitzy again was able to obtain some new tools for analyzing the global rigidity of finite frameworks. And these tools are very useful, and these were able to adapt to the periodic setting to actually attack some of these combinatorial problems in periodic global rigidity. So let me tell you what we do know. So what we have is an analog of the well-known result of Bill Jackson and Tibor Jordan, who gave a combinatorial characterization of global rigidity of finite graphs in the plane. And so here are the periodic analogs of their theorem. So there are two theorems here, because the first one deals with a case where the rank of the periodicity is 1. So it's only periodic in one direction, even though the framework is in the plane. And the second result here is where the periodicity has rank 2. And the conditions you see here in these characterizations are not very surprising. So they are sort of the periodic analogs of the Hendrickson conditions that you also see in the result of Bill and Tibor. So in particular, you see that redundant rigidity, or redundant periodic rigidity, is a condition. So this means that if you remove any orbit of bars, of course, the framework stays rigid. So this appears, and then also we of course have some connectivity conditions which disallow sort of local reflections of the framework. And these connectivity conditions are a little bit complicated. Let me maybe just focus on the case here where the periodicity has rank 2, which is probably the more interesting case. And let me give you a feel why we have these conditions here without actually formally defining these notions. So the conditions in this case will be in dimension 2 and have rank 2 periodicity are as follows. So the framework is globally rigid generically if and only if the quotient graph is connected. But it can have cut vertices. But if we look at each two connected component, so to speak, then it must be redundantly rigid. And we have two additional connectivity conditions. The first one is that the rank of this quotient graph of this component must be 2, so must have full rank. And we do not want to have any 0-2 block. So again, I don't want to define this formally. Informally speaking, a 0-2 block is just a subgraph of this gamma labeled graph that has rank 0. And it is separated from the rest by a vertex cut of size 2. And let me show you some pictures that I think make it perfectly clear why we need these connectivity conditions for global rigidity. So for example, if you have a 0-2 block, and you can see this here in the quotient graph on the right, as this graph here with the dashed edges, right? So here, if you look at these 4 dashed edges, then they all have group label identity. And so the rank here is 0. And we see that this dashed part here is separated from the rest of the graph by these 2 vertices. So this is a 0-2 block. Why do we not want to have that if we want to have global rigidity? Well, this rank 0 part here will lift, or will correspond in the covering to just a finite piece that is just repeated infinitely many times, right? And of course, because it's separated from the rest of the structure by these 2 vertices here, we can just reflect each of these infinitely many finite pieces locally to get another equivalent but non-congruent realization. Okay, so this is a very natural connectivity condition. We also don't want to have any component, 2 connected component, which has rank 1. So you see again here this dashed part. You can see that the rank here is 1 because of this walk up here. And it's separated from the rest by this cut vertex here. And again, this is bad because the cut vertex will lift to well, a line of vertices here, where you can reflect this dashed part, which lifts to this strip framework, right? So this strip framework corresponding to this rank 1 subgraph can be reflected in this line generated by this cut vertex. And of course, you can do this periodically across the framework to get an equivalent but non-congruent framework. Okay, so these are the cut conditions. I will not give you the proof of these combinatorial characterizations. It's a complicated proof, and I've talked about this before, but I wanted to mention this recent result. Okay, what else do we know about global periodic rigidity? Well, what do we know in higher dimensions? So if D is at least 3, we still have a necessary condition. And in fact, this is one of Hendrickson's conditions, right? So if you have generic periodic framework and the framework has not too many vertex orbits, so if the quotient gamma label graph has this condition here for the number of vertices, then if the framework is globally rigid, then it must be redundantly rigid. Okay, so this is an extension of Hendrickson's result to this periodic case in all dimensions. So this is one result. Combinatorial characterizations, of course, in dimensions D at least 3 are still open because, of course, again, they're also open for finite frameworks. So this is the latest result that we have here. We do have complete characterization now for periodic body bar frameworks in all dimensions. And so this is the main result here. So with Victoria and Chaba, we proved that if you have a generic periodic body bar framework, then it is globally rigid if and only if it is bar redundantly rigid. So if and only if it is redundantly rigid. And there's one small additional condition. The quotient gamma label graph must be of rank D if K is equal to D. So if the periodicity has rank equal to the dimension, then we need this small extra condition. But otherwise, the key condition here really is the bar redundancy. as is the case for finite frameworks. Okay, so this is a complete analog of the result of Bob, Tibor, and Walter in the finite case. Notice, of course, so we need this extra small condition here about the rank, because if the rank of the quotient graph is less than the periodicity, then you get these infinitely many subframeworks that are all disconnected. And of course, you can flip all of them to get a non-congruent equivalent realization. And they can still be vertex, they can still be locally rigid. Okay, so they could be bar redundantly rigid in particular. If, however, so k is less than d, and the rank of the quotient graph is also less than k, then you can also not be globally rigid, but you can also not be bar redundantly rigid. So in that case, you really only meet the bar redundant rigidity condition. Okay, so it's only in the case where k is equal to d that we have to make this small extra condition. Okay, so I would like to prove, or at least sketch a proof of this result. And the way we proved it is different from Bob, Tibor, and Walter. So instead, we used an idea that Kaszanitzy came up with recently, who observed that vertex-redundant rigidity implies a global rigidity generically in all dimensions for finite frameworks. And so our idea was to adapt that result to the periodic setting and then use that to prove this result about periodic body-bar frameworks. So let me explain this result. And this really is the main result, because the result about body-bar frameworks follows as a simple corollary of this vertex-redundant rigidity result. Okay, so let me talk about that a little bit. So first of all, the definition, of course, is exactly the one you would have guessed. So a gamma-labeled framework is L periodically vertex-redundantly rigid. So this is a bit of a mouthful. So let me just say it's vertex-redundantly rigid if for every vertex, of course, the graph G minus V is still rigid. Okay, so if you remove any vertex orbit, then the periodic framework still stays rigid. And the main result is that if you have a generic framework and it is vertex-redundantly rigid, and also if the gamma-labeled graph has full rank, if k is equal to d, then this framework is globally rigid. Okay, so we use a proof that is very similar to Kaszanitzy's proof, but there are some added difficulties that we have to overcome here in this periodic setting. In particular, so in the finite case, it is basically trivial that if you have small rigid graphs, then they are globally rigid. Because if the graphs are small enough and rigid, then basically you have complete graphs, and complete graphs are globally rigid by definition. In the periodic case, we still need a result like that. So we still need a result for our proof that says that if you have a small periodic rigid graph, then it also should be globally rigid. And in the periodic setting, this is actually no longer trivial. So you have to do a little bit of work there. And I will explain what we did to overcome this difficulty. And then there's a second issue. So Kaszanitzy's proof actually uses the fact that global rigidity for finite graphs is a generic property. So all generic realizations of a graph are globally rigid, or none of them are. And we don't know if this is actually also true in the periodic setting. So at the moment, it is not clear whether periodic global rigidity is a generic property. There's actually ongoing work with Kaszanitzy and Lewis on this, but so far, so this is still not known. It was certainly not known when we proved this result. Okay, so let me first explain how we overcome the difficulty of dealing with small graphs. So we want to show that graphs with few vertices are global, if they are rigid, are globally rigid. And the key idea here is to extend a result of Bezdek and Connelly. Okay, so a result that they used in their proof of the Kneser-Paulsen conjecture. And the key lemma here is the following. So this looks a little bit complicated and technical, but it's really not that difficult. So let me just explain a little bit what's going on here. So rather than you reading the whole statement in detail. So the starting point here is that we have two periodic point configurations in R to the D. Okay, and because we have point configurations, we can just model this as periodic frameworks with no edges. Okay, so you just have these periodic point configurations in R to the D. Then there exists a continuous deformation, which I call here P bar, that takes the configuration P to configuration Q, but this deformation is not an RD, but an R2 times D. Okay, so we double the dimension here, and we can then go from P to Q using this continuous deformation. And as we do that, the periodicity conditions are maintained. So I just added here these zeros here because now we have doubled the dimension. So we just fill up the lattice vectors here with these zeros. And importantly, all these distances between the points actually change in a monotone fashion. Okay, so this is the key lemma. The proof of this lemma is similar to the one that Bezdek and Connelly gave in their paper, but of course it has to be adapted to the periodic setting. But this is fairly straightforward. So how do we use this lemma to show that small rigid periodic graphs are globally rigid? Well, we do this in two steps. So first of all, a simple consequence of this lemma is this theorem. So if you have a framework that is not periodically globally rigid, then it is locally flexible in R to the 2D if you double the dimension. Okay, so the proof is very simple. So if you have a periodic framework that is not globally rigid, then of course you have two equivalent but not congruent realisations. So let's say Q and P. But then by the previous lemma, we know there exists a deformation that takes P to Q in R to the 2D, and it maintains the lattice, right? And because P and Q are equivalent, and because this continuous deformation in R to the 2D has this monotonicity property for the distances, all the edge length, of course, must be maintained. Okay, so this, of course, gives you the result. Okay, this is very simple. And then we get a simple corollary from that, which is the one we want. Namely, if you have a periodic framework that has very few vertex orbits, so the number of vertices in the gamma label graph is at most d minus k plus 1, then if it's rigid, then it's globally rigid. Okay. Proof again is very short, so we just use the previous result here. So if you take any D, capital D, that is at least as big as the current dimension D, and you look at any periodic framework in R to the capital D here, what can we say about the affine space, affine span of the points of this framework? We look at the vertex representatives, right? And of course, there are V of G of them. And so they can span an affine space of at most number of vertices minus 1. And then the framework is K-periodic. So the lifting, the covering framework has the property that the points span an affine space of dimension at most V minus 1 plus K. Okay, that's very simple. And our assumption here is that V plus K minus 1 is small, right? So it's at most D. Okay, so any periodic framework here with few vertices has this property that the affine span of these points here of the framework has dimension at most D. But now we are basically done, right? So if the framework is not globally rigid, then by above we have this continuous deformation in R to the 2D, right? But all our frameworks have affine span for the points at most D. And our assumption was that the framework is rigid in R to the D, right? So this is not possible. Okay, so such a deformation cannot exist. So this is our trick here to deal with this problem, to show that small rigid graphs are in fact globally rigid. Okay, so the second difficulty to overcome here is that we don't know whether global rigidity is a generic property for periodic frameworks. And here's the key lemma to work around this issue. This is actually a lemma that, or a version of a lemma that was in the previous paper with Victoria and Kaszanitzy. So the lemma says the following. Well, I need one little definition to state the lemma. So if you have your gamma labeled graph and you have a vertex, have a vertex v, let's say, then we can form, so this is my graph G, let's say, or G psi, this is my gamma labeled graph, here's V. Then we can form this new gamma labeled graph, which is GV, and we obtain GV by taking any pair of edges that leave V to vertices U and W, let's say, and just put in the edge from, sorry, V is gone. So let me draw it here. So we only have the neighbors left. And for any pair of edges that leave V, we just put in the edge here between the neighbors. When we do that, we just have to be careful that the label we give to this new edge, let's say this one here, must be such that when you look at this triangle here, so this triangle consisting of the two original edges with this new edge, then this must be of rank 0. Okay, otherwise, yeah. So this is the only condition. You just add these edges between neighbors of V. Of course, here could be parallel edges. So if you have two parallel edges and a single edge, then in this GV you would have two parallel edges with the corresponding edge labels. Okay. So what does the lemma say? The lemma says that if you have a generic framework with at least this many vertices, and you have a vertex that is of degree at least d+1, and the neighbors of that vertex, this is important, they span the whole space R to the D in the lifting, okay, in the periodic framework. And if the following two conditions are true, then we can guarantee that G is globally rigid. So we need the conditions that G minus V, so the graph that you obtain by just removing V without doing anything else, that must be rigid. And GV, this is this new graph that I just explained, where we add the edges among the neighbors, that must be globally rigid. So if that's the case, and the neighbors span the whole space, then G is globally rigid. So you can think of this as an extension of, or a stronger version of the one extension result, where we have the statement that one extension preserves global rigidity for finite frameworks, right? Because we have a weaker condition in some sense. Okay, so this is the key algebraic ingredient here. And again, I will not prove this lemma. It's not so easy to prove, but let's just take that lemma and the previous result on small graphs to actually sketch a proof of the main result. So here's the main result again. So we have a generic framework, periodic, and we assume it's vertex-redundantly rigid. And also if k is equal to d, then it's the quotient graph is of full rank, then the graph is globally rigid. Okay, so let me sketch a proof of this. The proof is not so easy, but I will sketch it on 2 or 3 slides or so. So the proof is by induction on the number of vertex orbits. If the number of vertex orbits is small, then, well, we have just seen that well, if the graph is rigid, then it's globally rigid. And of course, our assumption here is that the graph is vertex-redundantly rigid. So in particular, it's rigid, and therefore immediately by our previous corollary, it is globally rigid. So there's nothing to do. So what if the number of vertices in the gamma labeled graph is d minus k plus 2? So still small, but not extremely small. Then if you remove a vertex, then again, we have this count d minus k plus 1. And well, since we know by assumption that G minus V is locally rigid, right? By our corollary about small graphs, we know it's globally rigid. Okay, but if G minus V is globally rigid, then of course, this graph GV that I just tried to explain, where we add edges between the neighbors of V, then is also globally rigid, right? So we have that GV is globally rigid, G minus V is locally rigid. And so if all the neighbors of V affinely span the whole space, then we can just use this, this geometric lemma from just now to complete the proof. Okay, so the key remaining ingredient that we need to apply that lemma is to show that all the neighbors of V actually span the whole space, affine. Okay, and then the lemma will give us the result. So why is that true? Why do the neighbors of V span the whole space? So there are two cases. First case is very easy. So if D is equal to K, remember the number of vertices in our gamma label graph is this number. So if D is equal to K, then we only have two vertex orbits. So two vertices in the gamma label graph. But the rank is D, right? So that means that actually we have D plus 1 parallel edges. And so therefore, because of genericity, all the neighbors will span R to the D. So this is the simple case. If D is larger than K, then we have more than two vertex orbits. Okay. Again, we want to show that the neighbors of V affinely span all of R to the D. Suppose this is not the case. So if the neighbors only span R to the D minus 1, well, then let's remove a neighbor of V, let's say W. Okay. Then what can we say? So the remaining neighbors other than W must span a space of dimension at most D minus 2, because if they span a space of dimension D minus 1, then together with W, right, W must also be in that D minus 1 dimensional space by assumption, because our claim is false, then we would have a violation of genericity, right? So the neighbors except W must span a space of dimension D minus 2 by genericity, but this means, of course, that we can now rotate this this P of V around this D minus 2 dimensional space, okay, spanned by all the neighbors except W. But this, of course, is a contradiction to our vertex redundant rigidity. Okay, you can easily see that the space of non-moving points is actually of dimension D minus 1 at least. So this is a non-trivial motion that we get here by rotating P of V around all its neighbors except W. Okay, and of course, so G minus W is by assumption rigid, but here we have a non-trivial deformation. Okay, and the final case is that we have a large number of vertex orbits. So V is at least is larger than D minus K plus 2. In this case, the key claim is that well, the framework is so the framework GV is vertex redundantly rigid. So if we can show that, then by the induction hypothesis, GV is globally rigid. By assumption, G minus V is rigid. The rank of GV is the same as G by definition of GV. So all the conditions of this geometric lemma are satisfied, and we complete the proof. Okay. So the only remaining claim here is that GV is actually vertex redundantly rigid. Okay, and this we can prove very easily. So this is the last slide of this proof sketch. So here's again the claim. So this GV is vertex redundantly rigid for any V. Well, if it's not true, then of course there's a vertex whose removal gives you a flexible framework. Okay, but now if you look at the lifting, so at the periodic, at the covering, if you like, and we look at one occurrence of V, then the neighbors of V in this graph GV form a complete subgraph, right? This is by definition of GV. We have added all the edges among the neighbors of V, and of course vertices in the same vertex orbit connected automatically because of the fixed lattice. So that means that if we add V to GV minus U, then it's still flexible. Okay, because the neighbors of V here already form a complete graph. Okay, but this is a contradiction because, of course, G minus U is a rigid spanning subgraph of GV minus U plus V. Okay, so this gives you then the contradiction. Okay, so this is the sketch of this somewhat technical proof, but this is the main result, right? So vertex redundant rigidity implies global rigidity for periodic frameworks in all dimensions. And with this, we can now give our combinatorial characterization of periodic globally rigid Balibar frameworks. Okay, so this is again the result we looked at earlier. So a periodic globally rigid generic Balibar framework a periodic generic framework, body bar framework is globally rigid if and only if, well, it is redundantly rigid, and we have this extra condition that the rank of the quotient graph is D if k is equal to D. So how does that follow? Well, we already know that bar redundant rigidity is a necessary condition for global rigidity. It's also clear that if k is equal to D, then the rank of the quotient graph must be all of D. Otherwise, it cannot be globally rigid because you can flip all these infinitely many components in a periodic way. And if the framework is bar redundantly rigid, then it is also vertex redundantly rigid because all the bars connecting bodies are actually disjoint, right, by our model of a body bar framework. So bar redundant rigidity implies vertex redundant rigidity, but we have just shown that vertex redundant rigidity, of course, implies global rigidity. So this is the end of the proof of this characterization. Okay, I want to finish just by giving some tables of our current knowledge as far as combinatorial periodic rigidity is concerned. So here you see two columns, well, three columns. The last two columns here are the fixed and the flexible lattice. And in the first column here, you have the different structures and dimensions. So let's first look at the first table where we consider local rigidity. So if you're in the plane, then we have full combinatorial characterizations for the fixed and the flexible lattice established by Alyssa and Justin and Lewis. Of course, for bar joint frameworks in higher dimensions, this is open. And these, of course, are very challenging problems. For body bar frameworks with a fixed lattice, Kaszanitzy has the complete characterization, but all the other entries here, as you can see, are still open. So I think there's a lot of interesting work that can still be done here. And interesting work, I think, with important practical applications as well. And for global rigidity, so we just started to fill in this table. So I mentioned the result for D equals 2. So this is for the fixed lattice. This is the analog of Bill's and Tibor's theorem for finite frameworks. And again, for the flexible lattice, this is open. For higher dimensions, this is open. And the latest result that I presented here is the characterization for body bar frameworks in all dimensions with a fixed lattice. But yeah, lots of further work to be done. Thank you.
So thank you, Bernd, for the really interesting talk and the very nice result. So I guess at this point, I will throw it open for questions. So you have the standard two modalities, which is just demuting yourself and asking, or you can type it in the chat and I'll read it out.
I have a question. What happens if you allow yourself for a given configuration to use stress matrices for bar and joint periodic frameworks, like you can for the non-periodic case?
Yeah, exactly. Thanks, Bob. So, so previously we did not have this tool of periodic stress matrices, but there's ongoing work with Kaszanitzy and Lewis, originating from the recent meeting in California, where we establish stress matrices for periodic frameworks, both for the fixed lattice and for the flexible lattice. And so this gives us, of course, a new tool, and we're trying to use it to establish various statements about global rigidity of periodic bar joint frameworks and tensegrity. But at the time of writing this paper that I reported on, we did not have this tool of periodic stress.
But it wouldn't give a combinatorial characterization, but for a fixed, say, generic configuration.
Yeah.
You still, there's no, you don't know whether or not you can tell. Is that right?
Yeah, but we can extend basically your results. So with a periodic stress matrix, we can say if it has, you know, a certain maximum rank, then the framework is globally rigid, right? So these sort of results are the ones we're extending.
Mm-hmm.
And of course, we're also trying to extend the result of Shlomo and Healy and Thurston. and try to prove the other direction.
Yeah.
So we would have used. So I think we can prove. There's some details to be worked out. I think we can prove that indeed global rigidity is a generic property using these tools. But yeah, it should be. So we are writing this up at the moment, but it's not completely finished.
I mean, also, Bob, I guess maybe other people. So to my eyes, like somehow the flexible setup is more natural for stress matrices because they encapsulate a certain kind of affine invariance, which like the fixed lattice type setups don't have. And so in some sense, like, in some sense, in his setup, his tools are sort of better adapted specifically to that one, right? But if you look more generally, then the kind of stress matrix techniques, have like a more natural emergence in the periodic case too, right? I mean,
you're saying it's more natural if you allow the lattice to change.
Yeah. I mean, because, well, I mean, I learned from you, and the sort of importance of max rank stress matrices is that they fix some sort of affine structure.
Yeah.
Right. But fixed lattice rigidity doesn't really have affine invariance. You can't even rotate. Right. So it doesn't even have like full on Euclidean invariance. So
Yeah.
Right. So somehow it fits together not in as nice of a way.
True. Well, of course, the fixed lattice is easier to handle with the tools that we with the combinatorial characterization. Actually, the proof is very difficult. So it's of course an extension of Bill and Tibor's part, but okay, we need this extra lemma that I presented basically. So there's a lot of things going into that.